If we look at these three pictures of Obama, Justin Bieber, and Adele, everything looks normal at first, but when we flip them over, you can tell that something's wrong. We're so used to seeing faces right side up that when we see them upside down, it's easy to trick our brains. Neural networks can get tricked in similar ways. Take this example of a macaw. When you show this image to a neural network, the neural network correctly classifies the image as a macaw with 97% confidence. But then if we show the neural network this image, it's 0% confident that it's a macaw, so it really doesn't think it's a macaw. Instead, it's 99% confident it's a bookcase. So what's the difference between these two images? The first image is the original image, and the second image has had tricky noise added to it. So over on the right, we've got an amplified version of the noise. Normally this noise is much smaller, you wouldn't be able to perceive it if we didn't amplify it, but we're taking this tricky noise and adding it to the original image, so it still looks like the same image to us, but it tricks a neural network. As of now, there's no standardized metric for the robustness of your network against these tricky images. We've developed two metrics for testing the robustness of your network. The first is to take your original data set and add universal tricky filters to all of the images. So universal tricky filters tend to trick all networks, neural networks, independent of what kind of images you're classifying or what network you're using to classify. So these networks have been generated on individual networks. This one was generated on CafeNet, VGGNet, but once you've generated the filter, it tricks most any network. So our first metric is to just take our original test set and turn it into a tricky test set by adding these universal filters. The second is cross-testing, and that's where you generate a tricky network that would theoretically have a 0% accuracy on the network it was produced on. And then you cross-test, so you use that test to test another network. And then you take the test set of network B and use it to test on network A. So the analogy we like to use is you've got two high school teachers, Albert the art teacher and Bailey the biology teacher. And Albert writes an art exam and Bailey writes a biology exam. And then they give each other their exams and they take each other's exams. And then whoever scores a higher on the test is considered to be more well-rounded. So once we have our two metrics, then we wanted to test that on some real networks. So we came up with some simple modifications to a neural network that we thought might increase its robustness. So we had our control, which was a normal neural network, and then we had one that added universal noise to all of the images before classifying it, with the idea being to try and get rid of those tricky noise, those tricky filters that were added. So here's the adding random noise. The second one was doing PCA on the images before classifying them, and you can see that PCA blurs the image quite a bit. You lose a lot of the resolution, but it does do a really good job of getting rid of that universal filter. And the last idea we had was downsampling the images. So again, trying to just get rid of that noise. For our results, we found that the control did the best on the original test set. Adding noise did the best on the universal tricky test set. And PCA did the best when you considered if you considered both networks together. So for PCA, it really didn't care whether it was looking at the original test set or the universal test set. Adding noise, while it had the best on the universal tricky test set, still lost a bunch of accuracy going from the original to the test set, where PCA only lost a marginal amount going from the original to the test set. With our cross-testing results, you cross-test two networks at a time, and then you can get this lineup of who did best overall. So first we compared control and adding noise, then we compared control and PCA, then we compared adding noise and PCA, and we found that control was the most robust, adding noise was the second most robust, and PCA was the least robust.